Okay, so today we're going to go through the specimen paper for rings, polymers and analysis. This is a slightly shorter paper than the one that you'll be facing, but it's some good questions just to test our synthetic knowledge. So the first thing, it wants me to complete the following reactions. So this is good practice for your synthesis. You've got ethanol here, an aldehyde, and you're reacting it with tolerance reagent. They want structural formulae. So if you do that with tolerance reagent, you'll know tolerance reagent oxidizes the aldehyde to the carboxylic acid. So that will go to ethanoic acid. For the next one, you've got benzene being heated with concentrated sulfuric acid and concentrated nitric acid. So that's going to go to nitrobenzene, C6H5NO2. You've got a halogenoalkane here being heated with excess ethanolic ammonia. That means you place a bromine with an NH2 group to give you CH3, CH2, NH2, like so. So that's your synthetic route to get an amine. This, of course, is an ester, because you've got the two oxygens here, and you're heating it with hydrochloric acid. So you're going to undergo a hydrolysis reaction where you break this bond here. So your two products are going to be ethanoic acid, because you put an H there and an H there, and it will also be ethanol as well. And for this one, you've got phenol, and you reacted it with bromine. So hopefully you remember, this is actually the test for a phenol, and you'll hopefully remember that the bromine decolorizes, and you also see a white precipitate, and you make 2,4,6 tribromophenol. Your final question on this page, you take phenol again, but you react it with this guy. That, of course, is a diazonium salt. And you know, if you've got a phenol diazonium salt under alkaline conditions, that's going to give you a azodie. So I'm going to start off with phenol at the top here, and then you get your nitrogen link there, and that links to your benzene ring. So that nitrogen now goes there, and you link it on like so. Oh, right, okay, compound A here. This is an interesting compound, but don't let it freak you out. Just think about the functional groups that you've got. Okay, you've got a cyclic thing going on here. This is a ketone, isn't it? That's just a ketone there, because you've got carbon there, and C double bond O. This, of course, is an alkene, and this one may freak you out, but that is an ester. C double bond O, O there. So those are your functional groups. Deduce the molecular formula. Well, if you count it up, it comes up to C13 H20O3. Compound A contains several functional groups. Identify them. Name. I went through those. You've got a ketone, an ester, and an alkene. And then the next question. On the structure above, mark each feature responsible for the stereoisomerism with an asterisk and identify them. So the first obvious one is this one here. This is, of course, EZ isomerism, or old-fashioned cis-trans isomerism, because you've got a carbon-carbon double bond. If you think about it, you've got an H there and an H there, so they could be on the same side cis, or they could be trans to each other. The other two are slightly harder to spot. You've got that guy there, and you've also got that guy there. They are both optical. Why are they optical? Well, it's because you've got 4 different groups around the carbon atoms there. The final bit on this page is outline 2 important factors that we need to consider when manufacturing them. This one you should be familiar. It does come up a lot. You've obviously got side effects of the other optical isomer. One of them works, one of them will give you very nasty, well, could give you nasty side effects.
The other one is it's extremely difficult to separate the different types of optical isomers. So very expensive to separate them out. Right, so polymer time.
First of all, let's have a think about this polymer here. I've got it's just a carbon chain going along here. He has got to be an addition polymer. There's no ester groups, no amide groups, therefore he is an addition polymer. This guy here, you do have ester groups here, so he's going to be a polyester. First of all, first thing I have to do is identify not the easiest thing to do, do the repeat unit. Hopefully you can see that this is the repeat unit for the top one. For the next one, you're looking for where it goes, so if I do that bit there, hopefully you can see that you can just repeat that bit along there. In the boxes below, draw the displayed formula for these two monomers. Well, if I go back, what I'll do is I'll remove that box just to make it slightly easier to see. That there is going to become the diacid, and then you're going to put an H on here to become your diol. So you've got your dicarboxylic acid. And you notice it said display, so I've already made a mistake there. C-double-bond-O-O-H, like so. Where it says display, don't worry about your benzene ring, as long as it looks better than mine, which would be difficult. I'll just do a circle there. And then this bit here is going to become your diol. Again, I've done it. Like so. And then obviously you'll remember that these two would join together with elimination of water to give that. So break it at this bond here, your ester bond, and OH goes on this bit here, and an H goes on that bit there. So chemists have developed degradable polymers to reduce the quantity of plastic waste. Polymer D is likely to be degradable, or more degradable than polymer C. Why? Okay, if we look at polymer D is my polyester. We've just talked here about it being, that these are the monomers that you can prepare, and we know it can be hydrolyzed. So the first one, it can be hydrolyzed so the ester link can be hydrolyzed. The other thing is that this C-double-bond-O, hopefully you remember, is that this can absorb radiation and break as well. So C-double-bond-O absorbs radiation and breaks, and the ester link can be hydrolyzed. Okay, so this is an interesting one. It wants me to draw the tripeptide of these guys here. So I've got 3 amino acids here. The one that will freak you out would be this one, because it contains a ring. But let's just start off here. I'm going to start with that end there, and remember, let's just, I'll tell you what, let's draw him out. So this is going to be the tripeptide, so that's going to be the first one. It wants glycine, phenyl, aniline, and proline there. So glycine, like so, and then I do C-double-bond-O. That O there becomes that N there, and then just carry on. C-double-bond-O, and again, that O there becomes that N there, so that's going to be NH, CH, COOH, and then you've just got to link those two around like so. So it looks like that. Try not to let it freak out, just follow. It's going to be NCN, NCN, NCCN, NCCN. Yeah, NCCN. You get the point. Right, for the next one, it wants me to identify how many different tripeptides could be formed. What I've done is I've done a simplified diagram where I've just put R1, R2, R3.
So that's the first one. The next one I could swap those two around. Then I could put R1 from this end onto this end and swap these two around. So that's become R2 and R3 going on. And then the final two are where I've got R1 in the middle. So there's actually 6 overall. The easy way to do that is just put, it's actually going to be 3 times 2 times 1, which gives you 6. And that gives you the easy formula to use. Right, question on gas chromatography, mass spec. How do they work? The gas chromatography, when it goes into that, separates out the different components, so that purifies your compounds in a way. So shooting out one end of your column is just one compound. That goes into your mass spec, which will then analyse it, take the mass spectrum, compare it against a database of spectra, and tell you what it is. So the two things is gas chromatography separates it, mass spectrometry then takes it, it measures the spectrum, and then it compares it against other spectra, and it will identify the compound for you using that database.